period to meet available generation, you reconnect them back in the network during a valid period. So my methodology is shown on this slide. So the network which I analyzed is a modified IEEE 33 bus network. It has 32 load buses, which is made up of uncontrollable and controllable loads. We have bus 34, which is a grid supply point and is modeled as a slack bus, and the DG, which is also an artificial generator, which is a mathematical trick to incentivize the desired behavior of our loading curve. So in my case, I was planning to, the aim was to flatten the demand loading curve, but you could use any other form of shapes for shaping the network. So you could use any kind of desired loading curve. So then we move to the flexibility scheduling. What is flexibility scheduling? Flexibility scheduling aims to schedule flexible loads to meet available generation in the network, considering the payback potential. Now, what is this payback potential I've been talking about? Payback potential is the accumulated sum of shifted loads from previous time step. So what happens is, at a particular time step, when loads are being reduced during peak period, it is stored in the metric called payback potential. And at the next time step, if the load is still being reduced, it is increased. So the amount of loads that have been reduced in the next time step is added to the previously reduced loads. Then during a valid period where we can pay back or connect back this load, the payback potential shows the ability of the demand side management to reconnect previously shifted loads in the network. So which optimization model was I dealing with? I was working with a nonlinear optimization model using a software called MATLAB, and which was also embedded and MATPA. So what happened here was, the objective is to minimize generation cost. And what I also did was I scheduled flexible loads as negative generators so that we're able to minimize costs within the generator, and the flexible loads are now acting as negative generators. After the optimization model, we get the load dispatch. This load dispatch is how much load was shifted, how much load is being paid back, and how these loads are following the desired loading curve. The simulation runs a particular time period until at time which T, then it prints out the output and it ends. So if I'm going to be sharing my slides, so I'll be giving the organizer permission to share my slides. So this information of what I've already explained before. Okay. So I'll be talking about the case studies which I analyzed in this paper. So the first case study is called the case PG, and it's high flexibility volume from the participation of all load buses. So in this case, it was assumed that all the customers were willing to participate in demand side management. So they had a particular percentage of their loads which they were giving out for flexibility service. But for the second case study, which is case PG, we had like a relatively conservative volume of flexibility from the participation of selected group of load buses. So here, at a particular time step, only 16 load buses were available for flexibility, and the next time step, the next 16 load buses were available for flexibility. So in my work, that was what was analyzed in this paper, each time step was equivalent to about 30 minutes. I'll be sharing some of my results from my analysis. So on the screen, you could see the network loading measured at the grid supply points. So what is this network loading? What happens to the network when we have applied demand side management, considering scheduled load payback? We can see from this diagram that during peak period, flattening the demand load curve possesses greater challenge in case PG due to reduced flexibility volume compared to case PP. What does that mean? If we can see here, it was the loading before demand side management. Once we apply demand side management, for case PG, it reduced to this point here, which is the blue line. For case PB, which had all load buses participating in demand side management, it was closer to the demand curve, the desired loading curve, which is this straight line QF. And we can also notice that during value period that the payback in case PB nearly fits the load value compared to case PG. So based on this reduced loads here, these loads were paid back in this scenario. But for case PB, based on the reduced loads in this part here, it was increased in the value period to meet this desired loading curve. And I hope this makes sense to everyone. Please feel free to drop your question in the chat so that I can answer that after my presentation. The payback potential is shown in this slide, which is the metric in which I have developed. So you can see that the payback potential increases as loads were being shifted or reduced during peak period, and it reduces as loads were being paid back. So for case PG, it decreases to about 1.4 megawatt hour due to only 16 load buses available for payback. And for case PB, it reduces to about 0 megawatt hour, which shows that all previously shifted loads were paid back by that time step. This payback potential matrix helps the DNO to monitor shifted loads and those needed to be paid back and reconnected back to the network. One of the performance metrics which I also consider was the voltage profile. So in this slide, we have the minimum voltage profile. We could see that in both cases, case PB and case PG, all the load buses were within stationary limit. But we can also notice that there is a voltage drop before demand side management due to high demand in the network. But with the application of demand side management, it proves in alleviating this voltage constraint. So we can see now practically that demand side management does not only meet available generation in the network, it can also alleviate voltage constraint and also thermal constraint. As you can see here, it was at this point before application of DSM, but after demand side management for case PG, it was now at this point, and from case PB, it was higher. Why would we have different graphs for PG and PB? It was due to the flexibility available at different points. Remember that for case PG, we had only 16 load buses available at each time step, but for case PB, we had 32 load buses available for flexibility. So that's why we had the difference there. And the final result I'll be sharing is the maximum line loading. We could see that in both cases, they were operating close to thermal constraint. The maximum line loading was about 30%. But however, it is very important to highlight that the increased line loading during value period. If you notice that during value period, compared to the loading before DSM, when loads are being increased during payback, we see an increase in the line loading. So it underscores the importance of careful line loading consideration in load payback planning. What does this actually mean in real life? It means that once you are reducing load during demand side management to meet a particular generation, it is good. But once you are paying back this load, you should consider the line loading of your network in order to avoid valuation of thermal constraints. In conclusion, the metric payback potential has been shown to facilitate the coordination of load payback for different load flexibility volume and avoids network constraints violation and prevents new demand peaks, which means that we can now easily coordinate load payback while reconnecting shifted loads to the network without violating any network constraint. And also, we have seen that with the reduced load flexibility volume, which results to partially meeting demand side goal of load shaping. Well, it was actually evident from the case PG and the case PB. Now, we have also observed that with the increased flexible load availability, which may lead to issues like low voltage, like low voltages, higher line losses, and higher line loading during payback periods. What does this mean? It means that when we have more customers participating in demand side flexibility, we may have issues when we are paying back these customers with the low voltages and the higher line losses and the higher line loading. The concept of payback potential is now able to facilitate delayed network reinforcement. What does this mean? It means that instead of us investing more on additional generators in the network investing more on certain distributed generators like solar power plant and wind farm, we can also support the continuous operation of the network by investing in smart grid facilities like the demand side management, introducing the payback potential. So, which also now supports the smart grid and contributes to achieving the UK net zero goal. And thank you everyone for listening to my presentation. And that is the end of my presentation. Please feel free to ask your questions.
Thank you very, very much, Ms. Lois. That was such an amazing presentation. I learned sincerely. I took notes. I don't play with knowledge. I learned a couple of things. So flexibility is amazing, is great, but it needs a balance. From what I got, because of the payback potential. So I was wondering when you're talking, I'm like, but I thought flexibility was very good. And then you're not like, we need to balance it, because if it's too much, when it comes to payback potential, it brings about lower voltages in the grid, as well as thermal problems. Lower thermal. There's a way you put it, but I need to
Thermal
please
constraint violation, yeah.
yeah, thermal constraints, understand the voltage constraints violation. So that's really, really great. And I hope we all learned a lot. I would like for us to put down our questions. So what we'll do is you just put down your questions, and at the end of the session, she will come in and answer, so that we can keep to time, because we have another presentation.